Hey there, it's Miss Wesley here, and it is one of my favorite times of day because we get to talk calculus now. Today we're going to start a topic called implicit differentiation. It's a shortcut for taking derivatives that we'll actually be spending a few class periods on. And I'm at the start of a new packet, Diff Packet 3. I was hoping to use this video to walk you through some notes and get a good intro to the topic, and then we'll get to practice with it in class on the following days. So get yourself ready to take some notes. While you're doing that, a little joke comes to mind. This is an easy one. Speaking of calculus, did you know that a cow's favorite subject is calculus? I mean, that's just too obvious. Let's look at this warm-up. So it says describe the graph, and this is the first thing I don't like that I typed here. I say describe the graph of the function. But if I thought better of this equation that's given here and what its graph would look like, I don't think it would be a function at all. I think back to my days of conic sections, the good memories, and I see this as a circle, right? A circle centered on the origin of radius 4 when I see that 16 on the other side. So technically it's not a function. I guess if you were speaking technically, you would call it a relation, or a relationship between x and y. So I got a good idea of what the graph looks like. And then, like we've been doing over the past few lessons, we've been finding a rate of change expression. We've been finding a derivative, a dy dx. And we know what derivative means. Derivative means slope of the graph or slope of the tangent line at any instant. So we want an expression, given this equation, that could give us the slope of the tangent line at any point along that circle. All right, so we've got our setup here, and then we're supposed to find dy dx. But this is the first time, I'm used to seeing a bunch of expressions that we call them defined explicitly. Solved for y is by itself on one side of the equation, and you have all the other terms on the other side. And this technically isn't solved explicitly for y. So if I really were going to complete this warm-up and do it with the derivative rules that I know up to this point, I'd probably get y by itself. I'd solve this explicitly for y, get a y squared equals what? Negative x squared plus 16. And I would square root both sides. Takes a little bit of time, but not too bad. I got to remember the plus or minus comes on that side when I square root both sides of the equation. And I'd go from there. I'd have a job to do twice now, right? I'd have to find a dy dx, find a derivative with respect to x for the positive version of that square root and also for the negative version of that square root. But before I go do this entire warm-up, I'd probably need a little bit of chain rule here. I'm already thinking that we're going to need a quicker way. If the start of this packet, if you glance down the page, if it's filled with expressions like this, where you've got a bunch of x's and y's mixed in throughout the equation, kind of like the warm-up was, and if I take a peek down at the bottom, I see the warm-up again in another one of these. An equation like this, it's difficult/impossible to solve for y. It would be real hard to get y explicitly in terms of x. So this is where implicit differentiation is going to come in as a shortcut. It's not to say that I need it every single time I have an equation that's implicit. You see this example here. It says implicit form of this equation. This is a hyperbola. It says x times y equals 1. That's called implicit form because x and y are together on the one side. You don't have y by itself. But in this example, it would be really fast to get y by itself. We could divide both sides by x. And here I recognize this more as a rational function here, a 1 over x graph. And I could even think of it this way algebraically, so it'd be really quick to use the power rule and take a derivative, right? Get a dy dx, negative x, what to the negative second power, and you have your expression for the rate of change. But what about the equation here, and what about the equations that we see further down the page? Now what we'll do is we'll try this implicit differentiation on for size. When you're thinking of implicit differentiation, I want you to just think of it. I'm even going to write this here. It is just simply an application of a rule that we already know pretty well. It's an application of the chain. So I wrote this up here just to remind myself. We'll go through these steps in a second. I'll help explain it, but it really all boils down to knowing the chain rule to be able to use this method. So you'll recognize number 1 here. This is the same expression that we saw in the warm-up, our circle of radius 4, but we still haven't found the derivative dy dx. Implicit, if I'm following the steps here, says step 1, you're going to differentiate both sides of the function with respect to x. And here's the notation I'll put for that. I'll put d dx, derivative with respect to x, of the left side, so x squared plus y squared, has to equal now, well, if we differentiate the left side, we've got to also differentiate the right side. So derivative with respect to x, a d dx of the 16 on the other side. And these terms separately, just taking the derivative of the term separately, shouldn't be too intimidating. Remembering that we're taking a derivative with respect to x, because we'll talk about something special when we get to that y term. But really, what is this? I'm going to separate all three parts. I'm going to say this is the derivative with respect to x of x squared. This is something we've done before. Something new is a derivative with respect to x of the next term, so y squared, just separating those. And the other side, derivative with respect to x of a constant, the number 16, we know that completely goes away. That's going to equal 0 on the right-hand side, something that comes up a lot with implicit. Now, what's happening on the left? Well, I mentioned we've done stuff like this before. We've taken derivatives with respect to the variable x. I'm going to power rule this, and I'll call this 2x, nothing out of the ordinary. This is the part to focus on. This is the derivative with respect to x of a whole function, right? Y squared, which is a whole function in terms of x. This is where the chain rule portion is going to come into play. If I were just taking a derivative using the power rule of y squared, let's say with respect to y, I would power rule down the 2 and write a 2y here. But there's something else to think about. Y is a whole function in terms of x. So what we just did was we handled the outside portion of this. We handled the fact that y is being squared. Now it's time to handle the inside portion. We have to tag on, by the chain rule, the derivative of y with respect to x. Well, what is the derivative of y with respect to x? We don't know yet. That's what we're trying to find. So implicit says we tag on a dy, that should say dy dx to this term. And then we'll put equals 0 on the other side. You'll see that this becomes more commonplace as we try a few more examples, but the rule of thumb is that if, at least for these equations today, you've got the equation in terms of the variables x and y, if you're differentiating with respect to x, anytime you hit what's in blue here, anytime you hit a y term, that's when you'll be tagging on that dy dx. No other term got it. So now what do I have to do? Well, I'm supposed to solve for dy dx, right? That's the fourth step in the list of steps here. And so I see it on the left-hand side of this equation. Let me leave it on the left. So 2y dy dx. I will subtract the 2x to the other side. So equals negative 2x. And we're going to keep going. We got a little bit more to do to get dy dx all by itself. We want to divide both sides by 2y. So dy dx equals what? Negative 2x over 2y. And if anything can be reduced in this fraction, we would much rather leave it in simpler form. So what, the 2's can go away and I get negative x over y. This is our solution. This is one of the first times we're getting an answer for a derivative that's in terms of two different variables in terms of y and x. But that's okay. This is implicit, and the original equation was in terms of y and x kind of all mixed together without being explicitly solved for y. If we had to go further with this, if I said on this circle of radius 4, what's the slope of the tangent line at maybe this point here, this x and this y value, I could give a sample x and y, we'd need values. We need to plug in a number for x, plug in a number for y into this derivative expression, and you'd have the slope of the tangent line there. Taking a look at this second example now, I want to see if there's anything extra in here that we sometimes need to look out for, and I spot it. Look over number 2. Check out all the terms, see if there's a term where we probably have to think about something before we start. And I'm looking at this term here, the x squared y. All the other terms, the 6, the y squared, the y cubed, they're just single terms. I don't see products, I don't see quotients, but I'm going to put a PR here just as a reminder. This first part involves product rule. You have a function in terms of x, and x squared, and you have it multiplied by y, which is another function in terms of x. So we're going to start things off with that. I'm thinking in my head of u prime v plus v prime u for product rule. So I've got what? Derivative of, well, I'm taking a derivative. Let me write this here. I'll put d dx on the outside, just remembering to take the derivative of all terms on the left side and the right side. And starting the product rule, we need the derivative of x squared with respect to x. So that should just be 2x by the power rule. What do we write next to it? Well, we write v normal, or I should say y here, so times regular y. Notice I'm not tagging on a dy dx despite the fact that I put a y term here. I didn't take a derivative of a y term, right? I just recopied a y as part of the product rule. So then what's the next part? Then the next part has an x squared normal, so I'll just go out of order here and I'll write that next. And now's the part to be real careful about. We're going to take a derivative of y, but with respect to x. So derivative of just the variable y should be the number 1. But since y is a function in terms of x, like we said by the chain rule, let's tag on an inside derivative, which is dy dx, the derivative of y with respect to x. So that kind of handles, what's written in black there handles the first product rule part of this problem. The rest, for everything else, I just have to be mindful of when we're differentiating a y term. We've got derivative of y squared, so 2y, which is a y term, so it gets a dy dx when differentiated. Same thing with the next term, so I've got a y cubed to think about. Let's power rule it and make it 3y squared. And that definitely also gets a dy dx. And now don't forget about the other side. You have the number 6, the constant 6, right? We're taking a derivative of 6 with respect to x, so that should just be 0 on the other side. This is a common situation to find yourself in implicit differentiation, where you have this slew of dy dx's all over the place, and you got to get it cleaned up and solved for that dy dx. Best move to make is if you see a term that doesn't have a dy dx in it, namely this term here, we're going to move it over to the right-hand side, keep everything else on the left. And not only are we going to do that, but I also want to GCF a dy dx out of all these 3 terms. So to save myself a little space here, I'll write a dy dx on the outside of parentheses. And then carefully, slowly on the inside, let's see what we have left. We've got the x squared from the GCF coming out. We've got the 2y, so plus 2y. What else? We have the 3y squared. 3y squared, and then saving a step here because you could have shown this step too. It was just this underlined term that needed to get subtracted over to the other side. So I'll say equals negative 2xy. There is only one move to make to get dy dx all by itself. Now that we have a GCF, let me move myself out of the way and we will divide both sides by that trinomial here. We'll have dy dx, the derivative of y with respect to x, all by itself. And we're going to have a fractional answer again. So a negative 2xy can be your numerator. And like we said, we can divide by this string of terms. So x squared plus 2y, and then plus 3y squared. So while I might not say that this is the prettiest looking derivative we've ever taken, it wasn't too bad to use a little bit of algebra to get dy dx by itself, and it's pretty cool that implicit allows us to take a derivative of such a complicated looking function at first. And if we needed, I graphed this function just because I was curious to see what it would look like. Here it is here. If we needed the slope of the tangent line anywhere along this graph, we could plug straight into this answer expression that we got for the derivative. We'd need the x and the y to do so. And get the slope of that line without too much trouble. All right, stay tuned. We'll do a couple more practice problems and see how we start to like this method. Talk to you soon.